Case Western Reserve University's Institute for the Science of Origins proudly presents the Origins Science Scholars Program. The Institute advances the scientific understanding and application of the origins and evolution of human and natural systems. The Origins Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and MediaVision.
It is my pleasure today to introduce Janna Levin. Dr. Levin is professor of physics and astronomy at Barnard College of Columbia University. She researches black holes, the cosmology of extra dimensions, and gravitational waves. In addition, she is the director of sciences at Pioneer Works, a nonprofit cultural center in Red Hook, New York City, that builds community through the arts and sciences to create an open and inspired world. She's the author of 4 books for the general public: How the Universe Got Its Spots, A Madman Dreams of Touring Machines, Black Hole Blues and Other Songs from Outer Space, and The Black Hole Survival Guide, which is the title of tonight's talk. Take it away, Janna.
Thank you so much. I'm still not completely adjusted to this virtual reality, but it's nice to see you. I'm really delighted you invited me here to talk about the Black Hole Survival Guide. It's an interesting little object in the digital age because my friend, one of the reasons I love the physicality of it so much, it is very wee little, is because my friend, the great artist Leah Halloran, made original paintings for the book. So the book has over 20 original paintings. And every image you're going to see in this presentation is going to be one of Leah's paintings. This one kind of encapsulates a lot for me. Here is our poor astronaut. It's basically the title, who is veering uncomfortably close to the black hole and is probably in need of a good survival guide, a good set of tips for how to survive. One of the things I'd like to do tonight is to shuck away some of the misimpressions about black holes, some of the myths, and this kind of bad rep black holes have as weapons of mayhem and destruction, when in fact they're often quite benign. Black holes are actually quite small, and left alone, they're quite peaceful little places. So I want to shuck away some of the mayhem and those impressions before we do dig deeper into what black holes fundamentally are. And so one of the things I want to begin with is to dispel this idea that black holes are dense objects. A lot of people imagine, oh, it's a crush of matter, it's a dense crush of matter. But the reality is that there's nothing there. The black hole is nothing, it is empty. And so to begin, I want to emphasize that a black hole is as much a place as it is a thing. In fact, it's more of a place than it is a thing. It's not an object in space. The black hole is a space-time. And I want to begin, therefore, with space-time. Here's one of my astronauts who's floating around the Earth. And I want you to consider this experiment. If we're going to talk about space-time, it is a very challenging subject, but there's a sense in which it's intuitive. You can imagine performing the following experiment. Sit from the vantage of your couch and toss something across the room. Toss a baseball, toss a glass, throw your remote control. And you will notice right away that your freely falling object is not traveling on a straight line. It travels on an arc. Now, there's a little intuition there that I can imagine painting the paths of falling objects, freely falling objects around the Earth, and realize that they are tracing curved paths in space-time. That's a pretty crazy concept, but you could perform the same experiment from Australia, from Bangladesh, from any other part of the Earth, and systematically paint the shape of space by following the free fall paths that things fall along around the Earth. And that idea is hard to map to the next, but is in some sense intuitive. You can see it. You can see it for yourself. I think what is more challenging, and this is obviously Einstein's greatest achievement, is the understanding that it's not just space, it's also time. mass and energy warp not just the shape of space, they also warp time. So imagine you have an astronaut companion, and you and your astronaut companion are falling along these different paths in space. You will measure a different passage of time. Your clocks will not be in sync. You will not experience the same biological aging. You will have fundamentally different notions of the passage of time. And I think that is one of the hardest things that people wrestle with when they think about relativity. And we know that this is real. If you look at clocks near the surface of the Earth, they run more slowly than clocks in satellites in geosynchronous orbits. And we know that because you have to correct even your GPS unit for this relativistic dilation of time, the fact that time is not evolving at the same pace in these two places. Otherwise, you wouldn't be able to find Uber on a street corner. You'd be unable to find your driver. Now, this phenomenon of warping space and time applies to everything. It's not just if I throw things, it's even true for light. If I imagine shining a flashlight, I'm on my couch still, because we're all on our couches because it's quarantine. I'm on my couch, and this time, instead of throwing a glass across the room, which I'm getting some trouble for, I'm going to shine a flashlight. Now, light travels at this wonderful cosmic speed limit, the 300 kilometers per second nearly. And because it's traveling so fast, you're actually not going to notice, but light is also following a curved path in space. And this is not an experiment that we can do from our couches to get the intuition. It would be easy to imagine light seems to be unaffected by the curved space-time, but we know that it is. We know that even light travels on curved paths. And this is crucial for us, because if we're going to look for space-time effects and space-time phenomenon, we rely on light, which brings us most of our information about the universe. So here is an interesting experiment that was proposed in 1919. Actually, it was proposed earlier than that, but he first executed it in 1919 by Sir Arthur Eddington, the British astronomer who was an advocate for relativity. He was also a Quaker and a conscientious objector during World War I. And in 1919, he had this idea to try to observe whether light truly traveled along a curve in space. And the idea was quite simple. He imagined looking at a star cluster directly behind the sun. And if you look at something directly behind the sun, you shouldn't be able to see it. But his idea was that, well, if the sun, like all forms of mass and energy, are deforming the paths, the shape of space that you could paint by watching freely falling things in the universe, you should be able to see that the path of the light is bent by the presence of the sun. Now, if that happened, it would look to you like this star cluster was not hidden behind the sun, but was actually in a different location. And so this was a very simple experiment. There's one obvious terrible flaw, and that is that the sun is blindingly bright. So the idea was to go during a total eclipse to see if this star cluster was indeed behind the sun, as but visible, as predicted by this theory of curved spacetime. Now, it's just a coincidence that the moon subtends just the right size on the sky to completely occult the sun, blocking out the blinding rays and allowing you to see this thin vapor of light, maybe from this star cluster. He brings an expedition team. It's just 6 months after the end of World War I. He has a team in Brazil. He brings a team to Principe, a small island off of Africa. And the eclipse is already underway when they're under cloud cover and it's raining. Eventually it breaks. They're able to collect this observation. They're able to see the star cluster that they believe to be behind the sun, and thereby confirm the first experimental test of the theory of a curved spacetime. Now, this was symbolic culturally, not just scientifically. Here was an English scientist supporting the work of a German scientist, not 6 months after the end of this brutal war in Europe. And science was very much believed to be a way to transcend the kind of brutality and devastation that Europe had just been through. And I liken it to this idea, they came out of the shadow of the war into the shadow of the moon, and they emerged citizens of the same earth. And here Eddington becomes a proponent for this Einstein. It's headline news around the world. And he really catapults Einstein's fame in the English-speaking world and Sir Arthur Eddington becomes a real advocate for science. That idea that light travels on these paths is going to be important when we start to think about how to look at black holes. There are all kinds of different paths you can take in space-time. We know, for instance, that the ISS is on a curve in space-time. A lot of people imagine that the astronauts in the ISS look like they're floating because they're so far from the Earth. That is not the case. They're only a few hundred kilometers up. They're falling is what's happened. They're falling towards the Earth, but they're just going at such an incredible clip. They're going at 8 kilometers per second that they just never crash into the surface of the Earth. The astronauts in the International Space Station are falling freely along a natural curve in the shape of space-time around the Earth. And if you want to get up into space, you want to place something into that beautiful orbit, you have to be traveling at around, 11 kilometers per second to escape from the Earth, to be able to put yourself into these kinds of orbits. Now you can imagine, I'm sure you've heard, the denser the planet, the faster you have to travel to escape. So if I made the Earth denser and smaller, I would have to travel faster and faster to escape from the Earth. Eventually, if I made the Earth small enough, I'd have to travel at the speed of light to escape from the Earth. And it's so small, it's around 18 millimeters across. Imagine making the entire Earth 18 millimeters across, and you would have to travel faster than the speed of light to escape. Now, that means the Earth would go dark. You would not be able to see any light emitted from the Earth. And this really predates black holes, but what we now describe as the region beyond which you would have to travel faster than the speed of light to escape from a very dense system to be the event horizon. That's what we mean by the event horizon. It's really this shadow cast around a very dense system. Now, that might not happen. I mean, how you couldn't possibly crush the Earth to 18 millimeters across. That would be absurd and unphysical and impossible. But mathematically, it was just an idea. And during the time that Einstein was first publishing his general theory of relativity, he receives a letter from a friend who's an infantry soldier on the Russian front, Karl Schwarzschild, who is already an astronomer who has enlisted in the war. And between calculating ballistic trajectories, as you do, you're reading the proceedings of the Prussian Academy of Sciences. And in very short order, Schwarzschild comes up with this stunning mathematical solution. It was just an imaginary thought experiment. It was not meant to be real. He said, imagine I crush the mass, let's say it's of this planet, to a point. What is the shape of space-time around it? And he realizes you could orbit that crushed planet, you could safely stay outside of it, but as you got closer and closer, eventually you would reach a region beyond which you would have to travel faster than the speed of light to escape. And that is really what we mean by the black hole. We mean that event horizon. That's really what we mean. Now, it seems like I'm contradicting myself because I'm saying two things. I'm saying black holes are not dense objects, but then I'm saying a dense object is making a black hole. Now, what happened at this time was that Einstein actually believed we would be protected from their formation, that they wouldn't actually form. in reality, because you can't really crush something to a point. But stunningly, over decades, people realized that the thermonuclear energy, the same physics that was going into the attempt to build a bomb in World War II, was the physics that was responsible for the radiation, for the light of the sun, for the power and the heat of the sun. And people quickly realized, well, not quickly, actually, over decades, that eventually heavy enough stars would collapse catastrophically under their own weight. They would be unable to support themselves, and they would collapse to be so dense that they created an event horizon. You would have to travel faster than light to escape. But what was fascinating is after it creates this imprint in space-time, almost like an archaeological remnant, the star itself continues to fall, leaving behind a completely empty space-time. So when we think of a black hole and we think of this shadow, there's nothing there anymore. The star that may have formed it is long gone. Its fate in the center of the black hole remains controversial. We'll get to that. But in the interim, what we know is if you were to drift across the shadow of a black hole, it would be no more spectacular than stepping into the shadow of a tree. And there is literally nothing there. All that is left is a place, a space, and a shape. There is no dense object remaining.
We have one question in the Q&A, and so I usually read the questions, and I can't even ask the person who wrote it to read it for themselves because it's anonymous. So Anonymous asks, so it will be amazing if there is a computer graphics rendering engine that takes general relativity into account. So are there computer graphics rendering engines that take general relativity?
There are indeed. There are. I don't know how much are in the public domain, but I can tell you that there are the most excellent visualizations that I know of are by Andrew Hamilton, who is a physicist in Colorado, who writes very accurate codes of the behavior of particles around black holes, which includes light. So you can see all of the strange distortions and lensing effects. And he has a lot of wonderful videos online. So you should look up Andrew Hamilton. It's also my understanding that our friend, Glenn Kipthorne, who recently won the Nobel Prize and was one of the creative forces behind the film Interstellar, that those renderings were done very mathematically accurately at Kip's insistence, which sounds just like Kip. So they are very accurate models. When you see the black hole in Interstellar, you notice that they did this beautiful thing where there's this like disk of matter lighting up around the black hole because of the bending of the path of light, just like the eclipse. You can actually see behind the black hole, just like Eddington saw behind the sun. And that means you see this brightness above and below the black hole. And that's why you see the shadow. If that wasn't true, you could never see the shadow of a black hole. So those are my two favorite renderings.
I guess the Einstein, I mean, we heard from Dimitrios Psaltis last week. I guess that's all about doing such renderings. I mean, modeling what they were going to see.
With LIGO.
The Einstein Horizon Telescope.
Oh, EHT. Sorry. I have a little glitch on my audio here. Yeah, Dimitrios, EHT. Yeah. So exactly, Event Horizon Telescope is interstellar. The reason why Event Horizon Telescope took a picture, and I'll talk about it, of the black hole is precisely because the light from behind it allowed you to see above and below and allowed you to see the shadow.
So we have one more question, I think, before we go back to the talk from Bernice Kleiman. If the black hole is essentially empty, what happens to those planets and stars it has gobbled up, and astronauts?
Wow, I am, that is a big problem. So, and I hope you don't mind if I'm repetitive in my talk when I get to it, because I foresaw this question. One of the easiest conclusions, well, it's not an easy conclusion, but the direct conclusion of just looking just at relativity, just at the general theory of relativity, what it predicts, if you follow the math, follow the chalk, as we say when we're calculating on a board, the prediction is that all of that matter and energy will end up confronting what's called a singularity, a region of infinite curvature, infinite gravity. And in a finite time, it's as though the particles simply fall out of a cut in space-time. And that is an objectionable suggestion. So people like Roger Penrose, who recently received the Nobel Prize just in 2020 for his work on black holes, even in his influential paper that won him the Nobel Prize, he says, all of this matter is forced to fall. It creates the event horizon. It can no more stay there than it can the star that's collapsed expand outward at the speed of light. It has to keep falling, and it will go towards the singularity. But then he says, I don't really believe that. I believe that a theory or an understanding of the laws of nature that include quantum thinking about matter will modify this story, that the singularity is a false prophecy. Now, what replaces it is one of the most interesting questions in physics today. At this point, I'd like to give some survival tips. I mean, I think it's only fair and reasonable. This is really what it looks like to fall in a black hole. This is what people forget. They are dark against a dark sky. You could literally be an exploring astronaut in a region of the universe and not know. How would you know that you were about to approach a black hole? And so one of the suggestions is to bring a light source. Make sure you can illuminate that black hole. We know that black holes that are illuminated like this are visible. So here's an example where the artist has depicted hot debris and matter getting trapped in orbit around the black hole and lighting up. And so what you see is the shadow cast by the bright light source. Now you can't see the shadow of a tree if you don't have a bright light source. So what you're really taking a picture of in this idea of being able to see this is nothing. You're trying to take a picture of a shadow. Now, I would give you the tip that if you insist in falling into a black hole, that you should fall into the biggest black hole possible. When we look at the Earth, it does look like it's kind of flat. We're not flat earthers, but we understand that the Earth is so big that the curvature is not that imposing. And so the bigger the black hole, it's actually easier to it feels flatter. It's kind of easier to fall across a bigger black hole. So this idea that you would be torn apart and thrown into debris, you actually can survive the crossing of the horizon of a black hole. If I were to give you more advice, I would say to avoid the jets. So a lot of black holes that have debris around them, that have the opportunity to collect matter, will create such a storm in space-time that it will basically make like an astronomical ray gun. It creates a storm, not just in the space-time. Imagine a swirling, spinning black hole, and it's pulling particles from all around it. It could be stars that it's demolishing. One of the best ways we have of seeing black holes is to see them cannibalize a companion. A lot of black holes live in systems with other stars, and they can begin to pull tufts of the atmosphere of the other star off, almost like tearing off bits of cotton candy. And the material splatters onto the black hole. Some of it will create an accretion disk like that, but some of it will get churned up to these unbelievably high energies and create these spectacular jets, which I call ray guns, because literally they're shooting gamma rays and things into the universe. Some of the jets, depending on the size of the black hole, are so big that they can exceed the size of the entire galaxy in which they originate. And we've even seen pretty recently jets that punched out of one galaxy into another, blowing a hole basically in that galaxy, meaning vaporizing any planets or any exoplanetary systems that were there, including the possibility of any sentient life emerging on those planets. And so these are really powerful. So if you are an astronaut exploring space and you see the jets, stay a fair distance away. Just don't approach through the jets. Now, the other way that we see black holes was what we were just describing. The idea that the light, just like in the eclipse, is the path of the light is so distorted that even if you're only lighting up in front of and behind the black hole, that you can get a picture of above and below, that you can cast the shadow. And this is my artist's rendering of something that looks very similar to what Event Horizon Telescope managed, which was to take a picture of a black hole. It was very surprising to people that until a couple of years ago, no human had set eyes on the event horizon, on the shadow of the black hole. And it seems surprising because we talk about black holes and we talk about the existence of black holes, but we had seen all of them indirectly. We had observed them by cannibalizing their companion stars. We had observed them through jets, and we had seen them by stars orbiting what appeared to be nothing, but we had never actually laid eyes on the event horizon, which is weird because it's laying eyes on nothing effectively. Now, the Event Horizon Telescope worked by coordinating an international system of telescopes so that it worked as one big telescope. The reason why this needed to happen is because black holes are small. And this is also one of those myths that people don't really understand. Black holes are monsters. They're these gargantuan things. Black holes, the whole point is that they are spatially small. If I took the Earth and I made it a black hole, it's 18 millimeters across. If I took the sun and I made it a black hole, it's 6 kilometers across. It would fit in Central Park. If I took a core of a dead star, and this is much more physically accurate scales, and it was 10 times the mass of the sun, it would be a mere 60 kilometers across. So how could you possibly see a city-sized object at a distance of 1,000 light years that was dark? So black holes are incredibly hard to actually see. What Event Horizon Telescope did and announced 2 years ago was they looked for supermassive black holes. We have a black hole in the center of our galaxy. We call it Sagittarius A star because it's in the direction of the constellation Sagittarius from our perspective. It is 4 million times the mass of the sun, but it is less than 20 times across of the sun. Like, think about the sun on the sky. Imagine something 20 times across, 4 million times its mass in that tiny, tiny space, and then pushing it to 26,000 light years away. And now you have something tremendously difficult to observe. The other candidate besides Sagittarius A star was M87. M87 is a nearby galaxy. It has a supermassive black hole, 6.5 billion times the mass of the sun, but a staggering 55 million light years away. So even though it's solar system sized, it's much bigger than our black hole, it's further away. And the two of them, trying to resolve a picture of them is equivalent to trying to resolve a piece of fruit on the moon. So it's a very difficult challenge. And here was this beautiful reveal. I was out at the National Press Club in Washington for the reveal. We all knew what it was going to look like. We all knew that they had gotten this picture. The big surprise was it was M87. That was the picture that we got back, this neighboring galaxy. Now, if you want to be the first human to see a black hole with the naked eye, with the human eye, you'd have to get uncomfortably close. But what you would really be seeing is the twinkling effect of that black hole passing in front of, let's say, the galaxy and distorting the images of the light. And that's really what you would be looking out for. Now, I really do object to this kind of story of black holes as these weapons of mayhem and destruction. You cannot get very close to the sun, let's be honest. The sun is 1.5 million kilometers across, and it's really hot. If you tried to get closer, you would be incinerated. But you can get closer and closer and closer to a black hole because the mass is always in front of you. It's very strange. You never leave some of it behind. And you can get closer and closer. You could be a comfortable 60 kilometers outside the event horizon of a black hole and happily set up a perfectly safe orbit. And I think this is something that people misunderstand. They imagine you're going to be torn apart. You could quite comfortably, with your companion Alice, set up your own space station, orbit there for a while, and perform experiments, make observations, write your survival guide, make suggestions. One of the things that would be very interesting is if one of you wanted to explore. And one of the things you would find is if, let's say, you and Alice decide that one of you should go exploring and risk leaving the safety of your International Space Station, risk leaving the comfortable confines of your place there. You would find, let's say you decide to leave Alice behind and you decide to go closer to the black hole, even if it was not helpfully lit up with this background light, you would find that as you got closer and closer to the event horizon, it would seem that your time was slowing down drastically relative to Alice's. Now, from your perspective, your time is completely normal. From your perspective, it's Alice whose clocks are running strangely from the warping of space and time. For Alice, it's as though time seems to have sped up so much. Movies she'd be watching behind her in her transmissions would be going at a crazy clip. Music would be playing incredibly rapidly. She would be going gray in her hair. Eventually, even before you made it to the event horizon, Alice would die of old age. Imagine that she had set up some kind of system of infinite clones where she could replace herself with more observers, more scientists, and they could keep sending you transmissions. For you, it would all happen in a flash. And for them, it would seem as though you were frozen on the horizon. And that would be evidence, even in the total darkness of space, that you were, in fact, approaching a black hole. Now, I said that these dead stars was a way that nature thought of to create black holes by killing off a few stars. But it's actually not the only way to make black holes. You could make black holes in your laboratory on the space station. And you could make black holes, I mean, it would be hard. You can make, one of the arguments was that it would be possible to make black holes in some of the particle accelerator experiments that are happening here on Earth, that by smashing particles together at a high enough energy, you could actually get the kind of concentration to create a black hole. And I think even more interestingly, you can make black holes possibly in the primordial universe, in the early universe, primordial black holes that are no heavier than a pile of flour, but they would be significantly trillions of times smaller than a proton. So there again, the whole trick of black holes is to be small, but heavy. And even though they're not stuff, in some sense, black holes do not have to be made of things at all. You could simply imagine a universe that began and had primordial black holes that were not made of stuff. And yet they have heft. They have a kind of gravitational energy. So even though black holes are ultimately really a place, not a thing, they do a very good job of impersonating things. Black holes can orbit each other. They can move through space. But really what's moving through space is an absolute empty nothingness. And that is really exceptional. It's unlike any other phenomena in astrophysics, in the universe. And another, I think, really intriguing point about that is that black holes are somehow more like fundamental particles than they are like ordinary things. Black holes can be characterized just simply by very few parameters. You cannot make an imperfect black hole. And I think this is a really important point. If you and Alice are in your space station and you're performing these experiments about black holes, and you want to test them, and you decide to throw in a big mountain, and you think you're going to deform the black hole and you want to see what happens, that black hole will absorb the mountain, but it will shake off any imperfections, radiate them away until it settles down to a perfect dark black hole again. Black holes resist deformation. They resist imperfections. They insist on being perfect fundamental objects. And again, that is unlike anything else that we know of in the universe.
As you said, this is a really confusing concept because I think everyone thinks of, as Bernie says, the black hole as this Pac-Man running around swallowing stuff, wherever it finds you. I know people say, well, if the sun was a black hole, wouldn't it swallow the Earth and rip it apart? So maybe just go over that one more time. So
no, it would not. And it's beautiful. It's beautiful that even when Schwarzschild, so the term black hole didn't come around until 1967. So Carl Schwarzschild, who wrote to Einstein in 1916, who discovered the mathematical solution for a black hole, did not call it a black hole. They weren't really sure what they had, right? But what he did know, and what he did notice, which was quite gorgeous, is sure, if you replace the sun by a black hole tomorrow, our orbit is absolutely the same. It's fine. There is a tiny difference in our orbit, absolutely unnoticeable. We would be happily orbiting this black hole sun. I mean, it would be apocalyptically cold and dark, and that would be unfortunate. but no, we would absolutely not be sucked in like a vacuum cleaner. And the good example is the fact that we are in fact orbiting Sag A star. Sag A star is 26,000 light years away. It is 4 million times the mass of the sun. It is at the center of our galaxy, and we orbit that black hole, and it is not sucking us in. Now, one day we may fall into the black hole.
But we have time to prepare.
It's a the future is much longer than the past, is what I like to say. We are orbiting that black hole our entire solar system together is orbiting that black hole as surely as we, as one planet with our moon system, is orbiting the sun. And so, yes, the black hole has an important role on maybe sculpting the galaxy and defining how the Milky Way looks, on a lot of things, but it is our history. Really, it's probably sculpted our entire evolutionary history, and it may be our future. We may one day fall into that black hole, but it's going to take a very, very long time. And this is the defense that they have a bad rap, that they are not the weapons of mayhem and destruction. They are interesting in that they are the brightest beacons in the universe, despite the fact that they are fundamentally dark. And how do they become the brightest beacons? Is they churn up matter around them. None of it comes from the inside out. It's the ray guns, it's the mayhem that they do around them. But actually, we will live like this for a very long time.
So don't get too close, because then you could fall. You could cross in accidentally, but you're not going to get sucked in from way out here.
No, we're very far away. 26,000 light years sounds very, very safe compared to something that's less than 20 times the width of the sun. It's like a little marble.
I hope Bernice and everyone else is relieved. So,
I mean, it would be very hard for a black hole to give us grief. Very, very hard for a black hole to give us grief. It has to really come it has to be kicked out of a system and accidentally run right into us.
So there's Anonymous has another good question here that I'm gonna ask. So if someone can get really close to the event horizon, does that mean that they can experience the whole aging process of the outer universe, that they can watch the whole universe age?
It is fascinating. In principle, not exactly, but they can watch it for a very, very, very long time. So what actually happens is, as you approach the event horizon, you also have mass and energy, and you also deform space-time. So even though if I ignored you totally, I would say it would take you an infinite time to cross the event horizon. That's not what happens in reality. What happens in reality is that you deform the space-time. Literally, it's like the event horizon bubbles around you and absorbs you. Like you're like that little mountain that was deforming the black hole. And in that little time, the black hole will deform. But what it will do is it will ring off those imperfections until it settles down to a perfectly smooth event horizon again. And you have to think of it this way: no information can come from inside the black hole to outside the black hole. None. Because nothing can travel faster than the speed of light. And so information can be translated out. That means that that bubble, that deformation, cannot bear scars that tell you that it was me who fell in. It has to be able to settle down to a perfect black hole. It's the only possibility that makes sense. If the event horizon is really this one-way window, light can come in, but it cannot come out. And so, so after a finite time, which you can calculate depending on how heavy you are and how heavy the black hole is and how, all this stuff, you will officially cross, and even your friend Alice and her clone progeny will agree you crossed the event horizon. They will not believe you were there forever, but it could be a very long time indeed. You could find out what happened to the global climate crisis. You could see civilizations come and go. Maybe the sun bloats and distends and burns off the inner planets. Like all of these things could happen, and you could see them happening before you cross. Suppose you are a little less attached to surviving and you decide to actually make the trip. And so you jump in, you're seeing Alice age very quickly. She's seeing you age very slowly. One of the interesting things that can happen, and we've already sort of said this, is that your drift across the event horizon is unspectacular. We've already said there's nothing there. It's an empty space-time. It's nice and big, so you don't really feel uncomfortable. You float right across. My advice is to go into as big a black hole as possible because you will survive for the longest once you cross. You can no more, and I said this in the Q&A session, but you can no more stay frozen at the horizon. You can't hunker down there any more than you can travel at the speed of light. It's almost as though space-time is a kind of a waterfall. And this waterfall of space-time is dragging you down towards the singularity, if it exists. And so you are forced inward. I think a deeper and more profound way to say it is that according to Alice from the outside, she's imagining inside the black hole in the center, that's a place in space. But actually, and this is one of the things Sir Roger Penrose proved, for you, because of the relativity of space and time, because of the warping of space and time, imagine as you're approaching the event horizon, we said time seems to stand still for you. So what's next beyond time standing still? And that is time rotating into space altogether. And the consequence is that what Alice thinks is the center of a space in your perception of space and time is a future moment. You can no more avoid that singularity, which is in your future, than you can avoid the next moment in time. So the center of the black hole for you is in time, and you are going towards it. Now you can elongate it. You can make a really, really big black hole. You might be able to get a whole year out of it. If you fell into a black hole the size of the sun, you might be looking at microseconds before your demise. But if you went into M87 at 6.5 billion times the mass of the sun, you might be able to drag a year out of it. Now it would be an existentially difficult year. And you would have a lot of time. You could write that novel, you could send panicked transmissions, but your transmissions will never make it out again. And so you will face this quandary of whether it's worth documenting your experience and your discoveries inside the black hole. And I implore you to do so. just in the spirit of science, if you are the first to fall inside a black hole. Now, it's true that the event horizon is a one-way mirror, so that while the universe is dark on the outside of the black hole is dark to the universe. Outside the black hole, outside the event horizon, it can be bright inside. The black hole can be completely bright on the inside. All of the light from the galaxy that's falling in behind you, that you're seeing from the eons of the evolution of the entire universe, any light that can make it to you before you meet your fate in the interior, comes raining down on you and looks to you like this bright, it gets colorful, but as you get closer and closer towards this singularity or whatever replaces a singularity, it will be like a flash, a bright flash of white light. I sometimes call it a near death experience, the light at the end of the tunnel, except it's like a total death experience. We do know that while you can survive the transit across the event horizon, while it might be undramatic and it might be calm and it might be interesting and peaceful, eventually you will face some very uncomfortable hardships. As you get closer and closer to that singularity, you surely will be torn apart. It's as though your feet are being dragged towards the singularity faster than your head, your shoulders and your knees are being crushed together because the space-time itself is cinching. Your own matter and energy is now disturbing the space-time so dramatically that it creates a kind of storm. So there's no question you will be flayed, you will be stretched, you will be demolished, you will be torn to your fundamental bits. That fate is probably guaranteed, regardless of whether or not the singularity is real. You will be in dire straits. So there is no question there is a brutal, painful, all my defenses of black holes fade away at the singularity. I have to confess that indeed they will be weapons of mayhem and destruction at that point. Now, an interesting hypothesis has been that as you approach the singularity, instead of simply following general relativity's conclusions to the end, it has been hypothesized that maybe the singularity actually leads to a Big Bang. Now, the reasons for that are because they are similar. The shapes of the space-time are similar. You can, in some sense, make a quilt out of sewing the space-time of the black hole onto the space-time of the Big Bang. And that quilt can be made smoothly. Now, it's not a prediction, but it's just an observation that maybe what happens to your fundamental quantum pieces that are torn apart to its elementary elements, that you get blown out into a Big Bang, like a whole new ecosystem, and that you become part of a new universe that starts over again, that out of your debris, much as if your ashes were dispersed in the ocean, would become part of a larger ecosystem. And in that universe, maybe new black holes form and the whole process starts again, and new planets and sentient life and beings emerge. Now, cool thing about that is it's kind of like Doctor Who's TARDIS. It's as though the black hole is bigger on the inside than it is on the outside. If you remember Doctor Who's TARDIS, you go into the little booth and then there's this huge, exciting laboratory on the inside. The black hole can be bigger on the inside than it is on the outside. Imagine a black hole 60 kilometers across. It is the size of a city, but on the inside, it's the size of a universe. And that is one of the beauties that the curved space-time allows and permits. In the end, if you think of it that way, there is ultimately no surviving a black hole once you cross. There is one hitch, and I consider this to be quite insane and quite crazy. I do want to say that this idea of the black hole containing the Big Bang on its interior, the black hole having a whole entire universe inside, it's gorgeous, but it's not that well supported. It's really not, it's sort of fallen very much out of favor for for reasons that the laws of physics want something more stable out of a black hole than for it to be able to blow out a new universe every time something falls in. It would literally mean every time something falls in, it gets exploded into a new universe. And there's a sense of instability to that physicists argue against. And yet people still do not want to believe in this singularity. It doesn't feel good. There is something terrible about it. The idea that you could fall out of existence seems to violate the entire program of physics, which says that the world is knowable. You would essentially be saying that the world is unknowable, that it has holes in it, that things can cease to exist. I don't know of a physicist alive who believes that that's what happens, that's what happens. But I am going to give you a little glimpse of an even crazier suggestion that has gotten a lot of traction and a lot of attention. And the idea is this. The idea is that the interior of the black hole is connected to the exterior of the black hole by quantum wormholes. I don't have time to give you the details of quantum wormholes. And furthermore, nobody has the details. This is very conjectural and not at all completely understood. But it's an inspired idea. The idea is that when you fall into the black hole, as you're sending your transmissions, when you're flayed into your fundamental quantum pieces, that at the same time, they can be negotiated to the outside of the black hole through one of these quantum entangled wormholes. And in fact, ultimately, that there is no singularity on the inside of the black hole. Your information is not lost. Your quantum details aren't lost. They make it outside the black hole through these quantum entangled wormholes. Now, the reason why this is significant is because it means even your own death was prematurely declared. Because if Alice and all of her cloned progeny are allowed to wait outside the black hole for this to unfold, and they could collect all of those details of your quantum information, even though you were flayed and destroyed, that in principle, as unlikely and impossible a project it would actually be, but in principle, you could be reassembled from the information that was lost. You could be reconstituted. Even your transmissions could be reconstructed. Your lost novel could be found. And indeed, in that way, you could survive the black hole. It's the ultimate survival guide tip. Now, the amazing thing that I really want people to walk away with, besides understanding black holes are nothing, that they're bigger on the inside than they are on the outside, that they can be bright on the inside, even if they're dark on the outside, that they are not weapons of mayhem and destruction, that they're not huge, colossal monsters, they're actually quite tiny. Beyond all of that, I also want people to understand that black holes are in some sense fundamental to our understanding of the laws of nature, that they are completely unique in that way, and they provide us with a terrain on which we can understand what is next in the forefront of appreciation of this universe. The gaping problems that we still don't understand, like how did the Big Bang really happen? Did the Big Bang happen only once? Is the universe infinite or finite? Are things fundamental particles or are they strings? What is the nature of reality? All of these questions are playing out on the surface of black holes. These crazy quantum wormholes mapping the interior to the exterior of the black hole, if it's a solid idea, you can think of it as like tapestry, like as the way you sew threads together, embroidery, and you make an image that looks like a black hole, but on closer inspection, you realize are just the threads of your quantum entangled wormholes. In other words, the black hole itself might be defined by these really deep, really challenging fundamental processes. That the black hole itself on closer inspection might be a quantum phenomenon that's emerged and looks like a big object, astrophysical object from afar. But in reality, we realize it's just the overlapping quantum threads. And that is why black holes are so profound and fundamental. They really are the landscape on which we're looking at the most magnificent and confounding secrets of the universe. Thank you so much, everyone, for tuning in.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.